Good afternoon, everyone. I'm Wang Yanan from Information Engineering. Today, I'm going to give a presentation on my final year project, Reverse Hypercontractive Region of Binary Erasure Channel and the Correlation Bound. In this presentation, basically we will use the information measure characterization of reverse hypercontractive region to explore the region of binary erasure channel. The main problem we will try to solve is whether the correlation bound describes exactly what the reverse hypercontractive region is. First, let me introduce to you some definitions of forward hypercontractive region. Here is the definitions for forward hypercontractivity. A pair of random variables x, y defined on some probability space is said to be PQ forward hypercontractive for p greater or equal to 1 if this inequality holds for every bounded measurable function gy. The set of PQ satisfying this definition is the so-called forward hypercontractive region for this pair of random variables x and y. And here is an equivalent definition. The equivalent definition is related to two functions fx and gy, and this one is equivalent to the first one. The equivalence can be proven by Holger's inequality. Here p prime denotes the Holger's conjugate of p. Then is about the definitions of reverse hypercontractivity. Xy is said to be PQ reverse hypercontractive for p less than 1 if this inequality holds for every bounded measurable strictly positive function gy. This notation denotes the set of PQ that satisfying this definition, and is also the so-called the reverse hypercontractive region for x and y. Again, here is a similar equivalent definition. Xy is said to be PQ reverse hypercontractive if this inequality holds for every pairs of functions fx and gy, and here p prime denotes the Holger's conjugate of p. Then this is the graph for binary erasure channel. In this channel, bit 0 and bit 1 both have a probability of epsilon to be erased to 0 at the receiver y. Here I will introduce the concept of correlation bound. The correlation is a parameter of a channel is defined like this. And there is a strong relationship between correlation bound and the hypercontractive region. For forward hypercontractive region, for PQ inside the forward hypercontractive region, they must satisfy this inequality. For reverse hypercontractive region, the PQ must satisfy this inequality. These two are called the correlation bound. Here is a proof for the correlation bound to be necessary for hypercontractive region. Take the forward hypercontractive region, for example. The definition is like this. Then we will take gy to be this special function, and so this inequality will be transformed to this form. Then we will let fx equals to this expression, where the expectation of f0 is 0 and the expectation of f0 square is 1. And we will denote g0y to be this expectation. Then it's easy to see rho m square is exactly this expression, the supremum of expectation of g0 square y. By using the notations of F0 and G0, we could transform the inequality to this way. As the epsilon is very small, so we could use Taylor expansion to this inequality and ignore the higher order terms of epsilon. So we only consider the term of epsilon square here because the expectation of G0 and the expectation of F0 is 0. So by Taylor expansion, we could have this expression where the rho m square is the expectation of G0 square y. And by some simplification, we could see this inequality will be reduced to the correlation bound. So here we have finished the proof for the correlation bound to be necessary in forward hypercontractive region. For the reverse hypercontractive region, the cases are similar, only the direction are changed. So we will ignore the proof for reverse hypercontractive region case. This is equivalent characterization of forward hypercontractive. This is discovered by my supervisor. Basically, it talks about infinite alphabet settings. XY is PQ hypercontractive if and only if this inequality holds for every distribution Rxy that is absolute continuously to Pxy. Notice here we exchange the position of x and y just for the convenience of the following discussion. And this is a modified definition for the forward hypercontractive region for BEC. In the last summer, by using the characterization in previous slide, we have shown the following result. In forward hypercontractive region for binary erasure channel, the correlation bound is timed if and only if this inequality holds. And this result has been accepted by ISIT 2016 conference. Now we are going to explore the reverse hypercontractivity region of binary erasure channel. Again, we exchange the position of x and y in the definition. This is a modified definition of reverse hypercontractive region for binary erasure channel. Here is an equivalent characterization of reverse hypercontractive region established in finite alphabet setting. Is discovered by Salman Beji and my supervisor in 2016. The result divides the PQ into 3 cases and gives different representations for reverse hypercontractive region. 3 of them are expressed in divergence inequalities. And here is the result discovered on reverse hypercontractivity in my final year project. For XY distributed according to binary erasure channel, the reverse hypercontractive region is like this. When P is between 0 and 1, the Q's range is given by this inequality. When P is less than minus epsilon over 1 minus epsilon and this condition, the range of Q is given by the minimum value of these 2 expressions. When P is between minus epsilon over 1 minus epsilon and 0, the Q's range is not clear, but we know is a subset of this inequality. As you can see, this inequality is negative. The right-hand side of this inequality is negative, and the correlation bound is positive when P is in this range. So we could see in this case the correlation bound is not tight for the reverse hypercontractive region. Here is a figure showing the hypercontractive region of binary erasure channel when p is greater than 0 and epsilon equals 1/3. The green one is the forward hypercontractive region, and the blue one is the reverse hypercontractive region. Next graph is the reverse hypercontractive region for p is less than 0. Here the blue one is the case when p is less than minus epsilon over 1 minus epsilon. And this part is unknown. We only know it is a subset of an inequality. But we know this part, the correlation bound is not tight. So here we are going to the proof for the result claimed in the previous slide. According to the characterization, we will divide the proof into three cases. The first case is when p is negative and q is between 0 and 1. Then we need to find pq such that this condition will hold. But actually, the set for this case is the set of pq for this case is an empty set. That is, for any pq in this case, there always exists qx and qy, such that the following divergence inequality holds for any rxy with rx equal to qx and ry equal to qy. Here is the argument for the statement. We can let qx be, for qx we can let the probability of x equal to 0 be 1 minus delta. For qy we could let the probability of y equals 0 and the probability of y equals to be delta over 2. Then, for any rxy with rx equal to qx and ry equal to qy, the probability of x equal to 0 and y equal to 1 is greater than or equal to 1 minus 2 delta. As long as we take delta to be less than half, we could see the probability of x equal to 0 and y equal to 1 is positive. Then rxy is not absolute continuous to pxy, which means the divergence of rxy with respect to pxy goes to positive infinite. But the left-hand side of the inequality is still finite, so the reverse hypercontractive region for case 1 is just an empty set. Then here is the case 2. When p and q are both negative, we need to find pq such that the following condition is satisfied. That is, the minimax value of this divergence expression is non-negative. We claim that in this case, with these two conditions, we could claim that the above inequality in the previous slide, that is the minimax value of this divergence expression, is equivalent to the following condition. The q is less than minimum of these two expressions. First, we will prove the one direction. Suppose that q is less than minimum of these two expressions. Then we want to show the minimax value of this divergence expression is not negative. By using some appropriate parameters of rxy and qxy and qy and rxy, we could reparameter this divergence expression into a 3-variable function. We denote this 3-variable function as f2xrs. So basically, we want to show minimum over rs and maximum over x, F2 XRS is not negative. First, we will consider a case when Qy is interior. Then RS will fall into this range. So to show under these conditions, the following inequality mini-max value of F2 XRS is not negative. It suffices to show when Q is equals to this, and with these conditions, the inequality holds. This is because in F2, in the expression of F2, there is 1 over Q times the divergence times the divergence. The divergence is positive, so when Q increase, F2 will decrease. So we only need to consider the case when Q equals to the correlation bound. By lemma 2, we could see any interior minimax point of F2 XRS is also a stationary point. Then, by taking derivatives over XRS, we could obtain 3 equations. And these 3 equations are similar to that in the forward hypercontractive region. These 3 equations are similar to that in the proof of forward hypercontractive region, and we could use similar tricks to reduce it to one equation. Here is a proof for the lemma 2. It's very simple. We just prove it by chain rules. And then from lemma 3, we could know the one equation in the previous slide has only one root when p minus 1 times epsilon minus 1 over 2 is less than equal to 3 over 2. So we have shown under the condition Q less than 0 and these conditions, if Q is less than this inequality, Q is less than this expression, the following inequality will hold for any interior R and S. This is because root x equals to 1 is corresponding to the trivial solution when rxy equals to pxy. And under this case, F2 will be equal to 0 exactly. And this is the the only stationary point in the whole interior region. This is the proof for lemma 3. It's also very simple. We just prove it by taking derivatives. Then we need to consider the case when Qy is at the boundary case. There are many boundary cases, and we have checked every one. The only special case happens when r plus s equals to 1. And at this case, x can only be equal to r. So the F2 will be reduced to this form, and we want to show this form is non-negative for any r between 0 and 1. So we could obtain this expression. We could obtain this inequality. So by combining these two cases, we could prove the one direction. For the other direction, suppose the divergence inequality holds, then we want to get the upper bound for Q. This one is equivalent to the following inequality, so we could first by the correlation bound get one of the conditions, that is Q is less than the correlation bound. Then we just need to consider the case when Qy is taken as r plus s equal to 1. Then we could reduce f2 into a simpler form and then get this inequality. So the other direction is also done. Then for case 3, when p and q are both between 0 and 1, we want to find pq such that the following condition is satisfied. Claim that this inequality is equivalent to the following condition, to this upper bound for q. For one direction, suppose the upper bound for q holds. Then we want to show for any qx there exists rxy with rx equals to qx such that this divergence inequality holds. Or alternately, you can say we want to show the minimax point of this divergence expression is non-negative. Again, by some parameters like x, rs, first we need to then the divergence expression will be reduced to a function f3 xrs. First we consider the case when qx is interior. In this case, we want to show minimax point of f3 is non-negative. Again, by a similar lemma, we could show any minimax point of f3 must be interior and must be a stationary point. Then, by taking derivatives over x, r, and s, we could obtain 3 similar equations as that in the proof of forward hypercontractive region. And by reducing variables, we could obtain 1 equation. The root of this equation is corresponding to the stationary points of f3 xrs. From lemma 5, we could know the above equation has only one root, x equals to 1, for any p between 0 and 1 and epsilon between 0 and 1. Of course, this is in this discussion, we take q to be equal to the correlation bound. Actually, by the lemma in the following pages, we could see this expression is